Hi everyone, welcome to the first part of weekly supervised learning in computer vision tutorial. So today I will be talking about weekly supervised object detection. So we live in an exciting era for computer vision researchers. There has been constant progress in the multiple computer vision tasks in the last decade. So we have researchers have shown um, human level performance or better than human level performance in tasks like image classification, person identification. So we can say that two of the main driving forces in this progress were the deep learning, deep neural networks, and also large-scale annotated datasets. So, what do I mean by annotations? We typically need annotator to feed the computer vision algorithm with some annotations. Um, so, annotations can be in different levels. For instance, for typical image classification, the standard labels are image level labels, for example, motorbike and person in this example. And then annotations can be more detailed, such as annotating the centers of the objects, fitting boxes around them, object instances, and labeling all the pixels with their class categories. And so the trend here is as we ask for more details in the annotation time, the annotating time gets bigger, and obviously it gets more expensive as well. Um, so the current standard supervised setting has two problems. So the current annotated data sets are limited in terms of categories, so do not cover most of the object categories. And another issue is when we ask for higher detailed annotations such as pixel level, the dataset sizes or the number of categories gets significantly lower. So one way of um, moving forward is reducing our dependency to labels is annotations is weakly supervised learning. So very roughly, weekly supervision can be defined as using a lower degree of annotation or cheaper annotation at train time than the required output level at the test time. So, for example, um, if you look at the three important object recognition tests, such as image classification, object detection, and semantic segmentation in computer vision, um, so so the regular supervision can be defined as with this dash line. So simply source accesses showing the what kind of annotations are available during train time, and then what we are expected to output at test time. So the standard case have it has the same level of annotations during train and test time, and so the strong supervision is when we have a higher degree of or more detailed annotations during training time. And weak supervision is basically can be defined as so in train time we have less detailed annotations than the expected output of our predictor. So, for example, in the object classification task, I will talk about this in the rest of my slides, is so in train time, we are only provided image level labels, and in the test time, our goal is to predict bounding box for each object instance. So the goal of this talk is today to introduce the weakly supervised object detection problem and familiarize you with the problem and the challenges in this problem and key principles used in the previous works and state of the art, and maybe provide some future directions. Okay, so let's first contrast weakly supervised learning object detection to the related topics. So one of them is semi-supervised learning. So the here in this illustration, so we are showing the different supervision levels. So in the supervised learning, so basically all of our images are annotated with bounding box labels. In the weakly supervised setting, all of our images are labeled with only image level labels, and then we want to estimate bounding box at test time. So let's move to semi-supervised. So in the semi-supervised case, we assume that we have a set of images labeled with bounding boxes. We also have images not labeled at all; they're unlabeled. And so this is clearly different from the weakly supervised setting. But there is a hybrid approach. So if you have images labeled with bounding boxes, and then if you have images have only weak labels such as image level labels, so there are also work following this hybrid path, and so there are also methods working for weakly supervised weakly semi-supervised learning setting. So um, so my talk will focus on only the weakly supervised learning setting. So perhaps if you're a practitioner, weakly semi-supervised learning can be a more realistic setting. Um, However, the principles I will talk in the pure weakly supervised learning setting will be, some of them at least will be relevant and useful, hopefully, for the weakly semi-supervised setting as well. Another interesting and related topic is transfer learning. So you may have some regularly labeled images such as person and bike in this example with bounding boxes, but also you may have some categories only with weak labels with image level labels such as documents examples. So um, there is a line of work that learns object detectors from standard supervision, and then they learn to transfer this representation to with the supervised learning. Okay, so another maybe a bit loosely related topic is self-supervised learning, which has been quite popular in the last years. So it basically concerns about defining a task, such as predicting relative position of an image patch or rotation of images. So this doesn't require any manual annotation. So once the task is defined, we can train a deep network on that. But then we freeze these features or we use these parameters to transfer to downstream tasks. So I think the difference to weakly supervised learning is quite obvious. So at the end, self-supervised learning is typically, if it is for object detection, we use regularly annotated or bounding boxes to fine-tune these representations. So in the weakly supervised learning or object detection, we typically use pre-trained networks, like these are trained on ImageNet, and we do not use bounding boxes in our training. So I can also say that these two topics are complementary. Okay, so first I would like to introduce the weakly supervised object detection more formally and talk about what are the challenges in this problem. Okay, so so this is the setting in the object detection model. So we are given an image, a set of training images, and then we want to learn an object detection model, and our supervision is a class level label. It's motorbike in this example, sorry, image level label. So okay, so what can we say at least when we know that the image is labeled with motorbike in this example. So we can say that when this image is positive, so we know at least one object instance from this category isn't present in the image. So We don't know how many, but we know at least one. And if the image is not a motorbike, negative one, then we know that there shouldn't be any object instance from that category present in that image. So, okay, so these may sound trivial. Okay, so let's have a look at the assumptions. What can we do with this level of supervision? So we can obviously do supervision. So we can assume that there exists a set of features, or let's say parts, that are present in the positive images and absent in the negative images. Basically, um, whether we can find discriminative parts or features. And so we know that image classification for most categories works quite well. So there is a good proof for this. But also we want to localize the object instances to detect them. So the other assumption here is we also want these set of features or parts also present not only on the image, but also in the on the target object instances. So these features should appear on the target object instances. Also, it should be maybe spread over the whole object instance. So, okay, so I will explain this setting a bit more. So the um, the challenges in classification or generic object recognition is basically mostly due to the intra-class variations. So objects from a category varies can vary significantly in appearance. Their viewpoints, they can appear in different scales and aspect ratios. For example, if you look at these motorbikes images, you will see that they all look different. They all have different scales. They are captured from different viewpoints. Um, so other issues are obviously background clutter. So we can have very cluttered background. It may distract classifiers. And also occlusions. It can be self-occlusions or occlusions with the other objects. Okay, so these are the generic object recognition challenges. So what are the challenges specific to weakly supervised learning? Um, okay, so if you look at our assumption, so it's we assume that the same features are only present, the discriminative features are present on the whole target object instances. So, but this is not always the case. So, for example, if you look at these images, so these are all labeled as person category. And by just looking at this image, and if you define a common commonality between them, you may easily think that person class maybe should be maybe a face, or you may assume maybe person category means face plus an upper body. So in most examples, it is face and upper body. Only in one example, for example, here it is face and whole body. So, so in short, you can see that there is a big ambiguity here. So from image level label to localization. Another thing, another common problem is co-occurrence. So, for example, when we have this example images, so these are all labeled as terrain category, but you will also see that most of them have co-occurring context information. For example, rails, wires, and so you may easily think that it can be what is a terrain category. It can be rails, or it can be terrain plus rail, or maybe another option is the terrain object instance itself. So again, we have this ambiguity. Okay, so another one is sometimes we in some images for certain categories, for example, for animals, you see flocks of animals, such as so in this example, you see multiple sheep together. So it's very difficult to, again, define for a weakly supervised method to come up with what is the right category. So is it sheep means two sheeps, or it means sheep plus grass again with context, or it means a single sheep? Okay, so My message here is weakly supervised object detection is an ill-posed problem, and this is due to the part hole and also foreground background ambiguity. Okay, so let's have a look at what are the common failure modes in the weakly supervised object detection. Um, so uh, so this comes from a 2017 journal, and which uses some deep features. So it reports four kinds of failure modes. The first one is the hypothesis and ground truth, when object is not correctly localized, but predicted bounding box is in the ground truth. And the other one is when the ground truth box is in the predicted box. So you have a larger um, predicted box than the ground truth, but it is much bigger. So it's a wrong one. It's lower than the threshold. And we have also low overlap, so it partially overlaps the ground truth, and we have also some without any overlap with the ground truth. Okay, so most of if you look at the failure modes, you will see that most of them are due to low overlap. And so the interesting things here we will see is, so for example, we can easily spot this part versus whole problem in the so this basically appears in the hypothesis and ground truth failure mode. You will see that if you look at the samples, you will basically see that for person, cat, and dog, and so we basically learn a face detector instead of detecting the whole object. And so for the foreground background problem, we have categories which their categories are quite discriminative, co-occur with object instances. For example, sheep are usually on grass, boats are in the sea, in water, and TVs are usually in a living room with sofas or tables. So, and you will see that these usually occur in the when the ground truth is in the predicted bounding box in a much larger, or when we have some parts of low overlap and no overlap issues are due to the distracting background. Okay, so in this part of the talk, I will first um, talk about how we can formulate weakly supervised object detection in a learning framework. And then I will talk about what kind of principles we can use in this learning framework. Okay, so most of the weakly supervised object detection methods can be formulated in a multiple instance learning framework. So multiple instance learning is not specific to object detection or to this problem. So it's a generic setting which has been applied to before text categorization, predicting protein binding sites, object tracking, and so on. So the idea is quite simple. So receiving instead of receiving individually labeled object instances, we receive a set of labeled bags. So images are bags in this example, and we use regions as instances, but we don't have, so these region proposal, regions can be obtained via regional proposal methods. I will talk about it later. So the idea here is, for example, we do not have labels for the regions, but we have a label for the whole bag of regions in an image. So here, a positive image has again at least one. We assume that it has one positive instance, and it's mixed with the negative ones. And the negative bag, consists only negative instances. So our goal is to recover the true positive instances and in positive images, and then use them to learn a window classifier. Okay. So the pipeline. So the figure illustrates the pipeline here. So first, when we are given images, we need to generate bags to be able to use the multiple instance learning. So to do this, I will talk in the next slide how we can do that. So once we generate the bags or region proposals, we have to initialize the positive one. So we need to um, label one of them as positive at least. And then once we initialize our positives, now we can train our object detector, assuming that these are the correct ones, correct localization. Then once the object detection model is learned in the first iteration, we use the learned one to relocalize the positives. So it's kind of a self annotation scheme. Um, so uh, so this is common to this two-step alternating optimization is common to all weakly supervised methods and weakly supervised object detection methods. And so the challenges we have here is so when the initialization is, for example, that yellow box might be noisy, might be wrong. So when we initialize them with a wrong bounding box, then um, our method may converge to a local minimum. And the other problem I will talk in the next slides is, so what may happen is like, because we are learning the object detection model on the same images, and then we use this object detection model to relocalize the object instances, the model may overfit in the first iteration to the first initialized box and may not improve in the next iterations. So basically, overfitting. Okay, so let's talk about how we can generate bags. So we are given an image, we know it is labeled, but so we need to divide image into parts. So so obviously, if we have no idea where the object instances might be, so we can generate in a brute force way sliding windows. We can maybe in this four-dimensional space of translations, scales, aspect ratios, we can define a parameter sets and then generate dense set of windows. But the issue here is we may end up with too many, like more than 100K regions per image. So and so this can be quite expensive for a model to iterate. Okay, so another way of doing this is like smarter ways using object proposals. So these typically um, is methods like selective search windows, H boxes are different in Sprint. They are basically tailored to output regions with high probability objects in them. So I will talk about them in the later stage, but the interesting thing about these ones are they are sparse and they have very high recall in terms of objects. Okay, so once we generate our bag, then the second thing we need to do is initialize the positives then we can go on with the training. Okay, so one simple strategy to initialize is, for example, we can start with the whole image, label it as the positive, and so the advantage of this one is it's simple, and so you will, at least the whole image will include at least one of the object instances in it. But in the later works, some researchers noticed that after initializing the images with the whole image, sometimes the object detector may overfit to the whole image, and then the next boxes may stack the whole image in the next predictions. So Pandey and Rusakowski, because of that, simply proposed a whole image with minus margin. So this has been shown more effective in their work. There are also more sophisticated methods. For example, uh, constructing uh, graphs to find the initial boxes by song in ICML 2014. So the main idea here is to select a subset of candidate windows such that the nearest neighbors of the selected windows also correspond to the candidate windows in positive images. Basically, um, so we want the selected region's nearest neighbors to be in the um, um, positive images, to be discriminative. And also we want some diversity, not to only choose same nearest neighbor. So we want some complementarity in the to capture multiple nodes. Okay, so once we generate our boxes, initialize our positives, then the next thing is to learn the object detection model via retraining and relocalizing. The standard way of doing this one is, so once we have a model, so let's say our model is appearance model A here, and the proposal is encoded depicted as with B, and our image features are XB. So for the given proposal, so we can simply pick the highest scoring window by using argmax operation. And so this is one of the most commonly used method. So one of the disadvantage of this one is you can only pick one positive instance per image. There can be many in your image. Okay, so I will talk about it later. And so once we so when we want to learn, so once we localize the bugs, we want to learn a detector on it. So there are different ways of designing loss functions. So we may want, given the highest scoring window, to be higher than a margin if this is a positive sample. And then in the negative case, we want the highest scoring region to be smaller than a margin. So this is basically implemented as hinge loss in many methods. Maybe a more modern or more recent technique is basically taking the marks again. However, um, we take a soft marks over the other categories. So we want for that region to be high for the given category. And so we can use simply a cross entropy loss for it. And for the negative one, we basically want a high probability in the background category. Okay, so let's think about what is the difference to supervised object detection in this formulation. For example, let's think about faster RCNN. So in this setting, we are using a single positive instance in each image. So because we are taking the max, so maybe we are not using all the positives, and this may kind of reduce our positive set, effective positive set. And if you think about faster RCNN, most of the negatives are basically sampled from positive images, so around positive instances with low overlap. And this has been shown to be very effective. But in this setting, we use negatives only from negative images because it is too risky to sample negative instances from positive images because we don't have the ground truth and we may sample the wrong one and everything may go wrong. Okay, so one way of kind of reducing our risk is basically hedging our bets on the multiple proposals. So instead of maybe max scoring proposal, um, we should pick a selection of them. And so one way of doing that one is basically using a relaxed max operator, or it's also called softmax as well, but it's not the softmax using the deep learning toolboxes these days. So the idea here is basically we take logarithm of sum of exponentials of the scores. So this means basically this kind of um, gives more weights to the even more weights to the higher scoring ones, but it doesn't give zero weights to the lower scored regions. So one of the advantage of using this is it is less sensitive to initialization, because if you do a mistake in the beginning, it's not as important as the max operator, and also it can still use multiple positive instances during training time. And for example, if you look at the models trained with the max margin optimization, you can see that object categories like object instances and cow category are grouped together usually. Um, and if you use this relaxed version, you can see that so the red color is showing the more confident detections and blue are the less confident ones. So you can see that object instances are detected more successfully with the relaxed version. Okay. Another key idea, which is more robust to kind of doing mistakes in our training time, is inspired from curriculum learning, so which comes from human learning basically. So the key intuition is we start with when we learn something, we start with easy examples and then we move to harder ones later. So this principle has been applied to weakly supervised object detection by Kumar et al. In NERPS 2010. So the idea has been so we we first want to um, detect the objects, use their positive instances to train our network or to train our detector initially, then gradually move to the more difficult examples. So the problem here is how do we define the easiness and difficulty level? And what Kumar has done is basically um, they have checked the um, confidence or the score for each window, and then start with the high scoring ones and move to the lower ones. And this has been also shown for um, different measures for difficulty or easiness. So, for example, another way of looking at this is like smaller samples can be more difficult to detect because they have less details, less resolution. So, uh, Bilan and Shi in 2014 showed that if you start with bigger regions and then move to smaller ones gradually, this improves the performance. And finally, a more sophisticated method is basically via inter-class competition. So Sanguinetto showed that we should first choose the we should first start with the categories which are more confident. For example, in this example, TV is more confident than the car, so you start with the TV detection first, then move to car detection later. Okay, so um, another elegant idea comes from CVPR 2014 Jimbish paper. So the observation here is the detector may overfit to the given proposal, given positive instance after the first iteration, may not refine in the further iterations. So the solution is quite simple. The solution suggested. So the idea is we divide our positive image set into multiple faults. So I'm showing two subsets in this example. So what we do is in the subset 2, we from subset 2 and all the negatives, we train an object detector 1, and then we also train object detector 2 in the subset 1. So it's a cross training basically. Then what we do is after this training stage, we use the object detector 2 to um, detect the object instance to label the positive basically. So the key idea here is when we use the same positives to train retrain and relocalize. And if we have a high capacity model like a CNN deep network, which may easily overfit to the first or given proposal, and this may not change in the further iteration. So the idea here is, um, yeah, so we use um, different images to train, and then we use the detectors to relocalize. Okay, so another way of improving relocalization is introducing some soft constraints. For example, in the window selection process, we have usually 3,000 windows in each image. So we may want to eliminate some of them or put some constraint on the selection process. So one cue used in this for this goal is pairwise similarities. Um, the sellers have shown in ECCV 10 that so such similarity pairwise similarity. So the key idea here is the object instances of the same category should be similar to each other in some feature space. So they have shown that simply the pairwise similarity can be modeled with a fully connected CRF where images are the nodes and states are the windows. So basically, the goal is to find a high scoring window. So unary terms are coming from the objectness scores. We want high objectness score, but we also want the selected windows to be close to the other selected windows in other positive images. So um, this is they have shown very good results, shown that there is less overfitting in this method. But I think the cons of this method was it was a bit expensive to optimize because of the fully connected CRF, and also it ignores the intra-class variations because maybe some instances may be similar to each other, but some may not be. Okay, so um, basically. Addressing the last concern, so better ways of modeling intra or in-class variations is basically can be done by clustering multiple similar-looking object instances, and this has been shown by Wang that so we can simply cluster some of the instances together, um, and we may find some basically subcategories and then kind of enforce some similarity between one of the subcategory to each positive instance. So this has shown very impressive results at that time, and it was more successful to model the intra-class variations, but the number of clusters in the use clustering method, it was very sensitive to that number, so the detection performance was largely affected by that. Okay, then another way of thinking this one is we can also, instead of clustering, we can use exemplars, so choosing basically representative samples. So, and this has been shown also to be quite effective. So in this example, you can see that, for example, the the exemplars for jet fighters and passenger fighters are used to enforce similarity between only the right subcategories. Okay, so another cue we can use to improve relocalization and retraining is modeling the context. So context can be basically modeled separately in a way that so we have a separation between foreground and background. And Rusakowski in ECCV 2012, for example, models the foreground and background with two different boxes and show that this works better than just using a single box to separate object from background. And then Kantorov took this further and then shown that the method takes an expanded ring around the foreground, and the key idea here is there is contrastive guidance used, and it encouraged the predicted object region to be outstanding from its surrounding context. And um, this can be encoded by maximizing the difference between the class score of that object region and that of the surrounding context, basically. Okay, another, I think, very important cue which help with the ambiguities we have is the objectness. So first time proposed by Alexa. So objectness is a measure of basically likelihood of a box containing an object or not. And it is object agnostic, so it's not specific to object category. So and also the other maybe more successful works built on this one is selective search and edge boxes. So basically, most of them uses low-level image cues such as saliency, contrast, edge density, or superpixel straddling, and so it has two benefits using objectness. So one is basically we can use them to eliminate some of the object proposals, so we get some um, high recall, small set of high recall object proposals. The other thing is we can use the objectness score also within our detector, and so this can help us to steer the relocalization or detection toward objects, and it can also eliminate the detector to pick the ones from background, basically. And it has also another benefit. It can also prevent the object detector to pick parts instead of whole object as well. So this is very important. Um, Another simple principle is equivariance. So we want our predicted output to be equivariant to the transformations applied to our input image. So in this example, you see at the top image with two cars, and then in the bottom one you see that the same image is filled. So if we apply a method which is trained on them without any constraints or regularizers, so you can see the heat map. Red shows the more confident detection. So you can see that, so at the top one, the black card is detected confidently, and in the bottom one, the right one is detected. So the blue one is detected confidently. However, what we want is what we know a priori is so um, they should be equivariant. Basically, if so by simply minimizing the KL divergence between these two feature maps, um, it can be the so the last heat map is showing that we can learn object detectors which are more confident in the previously, which were not confident in the instances which it was not confident before. So you can see that the yellow or blue regions are more towards red color or orange color now, more confident. Okay, so another pride I partially mentioned in the previous slide is the scale. So she in ECCV 2016 use size estimate. So basically, it trains a size estimator from subsets of training sets for object instances, and then use this size estimates to determine which order the images should be fed. So start with the bigger ones and then feed the gradually smaller boxes. But also, it uses the um, simply the so they use this predictions from size predictor to weigh the object proposal scores. So if the box has high score and also the it matches to the estimated size, then it gets a higher score. Okay, so another, I think, maybe orthogonal to most of the things I have been talking is using the motion. So obviously we are not limited to still images. We can also use weakly supervised object detection in videos. And the basic principle here is pixels belonging to an object instance move together. And so then what is shown in this paper is basically, so if we use accurate motion segmentation, we can get quite accurate object proposals or spatial temporal tubes in this example. And then we can refine them by using objects. And then we can use the refined tubes to train our object detectors. And then we can use the trained object detectors and apply them to still images as well. One of the problem, quite I think important and interesting, is the domain gap between the images and the videos, because videos have all this um, compression artifacts, sometimes the lower resolution, motion blur, and such problems. So the authors in Press CVPR 2012 show that a domain adaptation that adapts the object detectors trained on the videos to still images improves the object detection performance significantly. Okay, so just to summarize, so far I have discussed what is done for. I have discussed first of all, most of the weakly supervised object detection methods can be put in the multiple instance learning framework, and then the common steps are generating windows, initializing the positive, and then doing this two-step alternating optimization to train and relocalize the object instances. And I have mostly summarized the previous work, how we can improve the initialization, relocalization by using priors and other additional cues. So in the rest of the talk, I will move to more recent work. So in parallel to the advances in the computer vision methods, um, so the common trend basically which learns deep models in an end-to-end way, and that shows that these improve quite significantly over the methods that use deep network as black box. Um, a similar trend has been followed in the weakly supervised object detection. And the first method follows this trend is weakly supervised deep detection network, WSDDN. So, so the contributions are the contributions of this method is it was the first end-to-end weakly supervised object detection method. So the previous work was using pre-trained CNNs by freezing its parameters and then just as a black box feature extractor. So this work has shown that we can instead fine-tune a pre-trained network for the weakly supervised object detection task. And the authors simply use the ROI pooling from Faster RCNN Gershik ICCV 2015. And the other contribution was a novel two-stream architecture which does classification and localization. So the idea is illustrated in the figure. So it starts with an image, and then the image is fed into convolutional layers. After some convolutional layers, we use region proposals to extract features from the convolutional map, feature map, and then each uh, feature corresponding to the region proposal fed into this two-stream network. So the two-stream network in the first part, it in the first part, it classifies each region to a category. For example, so the regions are color coded here. So you can see that. So for example, R1 is yellow here. So R1 is assigned either to horse or person. So basically, it's a softmax operation normalized over the categories for each region. So the localization stream, um, um, so given a class, for example, for horse, it picks the most promising region. So how this is done is, again, there is a softmax operation, but this time it's over the region. So for each region, it picks the most promising region. So once we compute both the probability maps, they are element-wise multiplied, and then because we have only an image level label, they are summed over the region, so such that we get one score for the whole image per class, and it's done with the binary cross entropy loss network is minimized. Okay, so um, the the interesting thing about the method WSDDN was it had a significant leap over the previous methods in terms of results. And it was the first one using end-to-end learning, and it didn't have any customized deep learning layers. So when we look at the failure cases, we can see that at the bottom, the still WSDDN is detecting parts. Like a face detector here, again another face detector, and also it was grouping object instances together. And if you look at the algorithmic limitations, you can see that it doesn't, again, because of the softmax operation, it doesn't really leverage the positive instances in positive images much. So it usually use one or very few instances, positive instances during training. And another limitation was so it doesn't exploit negative instances in the positive images. So if you think about faster RCNN, all the negative instances are sampled from positive images. So those are the regions overlapping with basically positive instances with a low overlap ratio. And but this is very tricky in the weakly supervised object detection, because if you choose the wrong negative, then this may kind of degrade the performance greatly. And the other limitation compared to the faster RCNN was it didn't have a bounding box regression, so it was limited to basically the proposals and object proposals. It couldn't refine them further. Okay, so the next work I'm going to talk about is addressing one of the limitations. So WSDDN is basically classifying images based on some implicit instance scoring. It's doing back classification. It's classifying the whole image via scoring the instances. So online instance classifier refinement instead builds on the WSDDN, but it used the WSDDN to kind of score the regions and then picks the highest scoring regions and then learns instance classifiers on the region. So it's not an image classifier anymore. They have instance classifiers, and um, they refine it multiple steps, each instance score. And the authors show that such a strategy helps with um, moving from small parts to larger object extent. Okay, so the same authors observed that so this is instance classification is a good strategy, but still we do not use all the positive instances in an image. So in the image here, what what is it showing is that in the conventional multiple instance learning, um, so we have a batch of instances and we assign one label to them. So what they propose in C here is simply generating multiple clusters around the high scoring windows. And so in this example, for instance, they have multiple bags. So for example, motorbike and car, and for the door, they generate different clusters. So this way they can um, leverage the more positive instances. And so um, so how this is done is with basically building a graph over them and simply picking the regions with most connections to the cluster centers. Okay, so as a final work, I will talk about the state-of-the-art methods in weakly supervised object detection currently. So it has multiple components, but I will specifically talk about one of them. So the paper focuses on the partial ambiguity, and the idea here is it proposed a regularization component is called concrete drop block to regularize the network to lock into small parts of the object. And so the authors introduce this customized drop block, and so which is a data-driven and parametric dropout basically. The idea here is to kind of pose a adversarial game, and the idea here is the concrete drop block parameters are optimized, which is shown with theta here, to confuse the image classifier by dropping the most discriminative parts, and this pushes the object detector. The loss function is shown with L ROI. Its parameters are W, basically pushing the object detector to look for more evidence rather than single part, and move to the rest of the object and to cover the whole object in the detection. So this is also some very elegant way of building such a regularization to address the part and whole ambiguity. Okay, so so far I haven't talked about the results, and in the last slide I'm showing the performance in terms of mean average precision at 50% intersection over union for the previous work. So this is in Pascal Book 2007, and so on the right hand side I'm showing the relative performance compared to the regular object detector. So the relative performance of weakly supervised object detector to the regular one. So the first group of work has been using CNN with so AlexNet, Preter and AlexNet as a black box, and the performance were up to 60% almost. Then WSDDN has really improved the weakly supervised object detection with the end-to-end learning, and so then the next line of the work that I have discussed most of it in my slides is use better networks, but also instance classifiers and effective regularizers. And I can say that there has been a remarkable progress in this problem. So the state-of-the-art RAN CVPR 2020 is approaching to 80% mean average precision, 80% of the um, um, relative performance of the standard object detector. Um, okay, so then the question is, are we done? Is it end of the story? It is obviously not. So we always aim to improve, further improve. So then the question is, what can we do more? And so here I'm showing, visualizing the results of the state-of-the-art detector, vehicle supervised detector. So we see on the first three columns, we see successful object detections. But on the right column, so we see that still object detectors are, weakly supervised object detectors are suffering from detecting parts. So in the, for example, especially in the second image, you can see that it's basically a face detector. And also we see that in the surfboard category, it's still detecting the context. So there is again foreground background ambiguity. Okay, so I think the most important take-home message I want to deliver today is weakly supervised object detection. Perhaps many weakly supervised learning problems are ill-posed problems, and in my case, it's ambiguous due to the partold and co-occurrence issues, foreground, background, and grouping problems. Um, and also, I think most weakly supervised methods are their training are sensitive to initialization and prone to overfitting. So these are the common limitations, and I think we have been quite successful as a community to address um, partially these ones, and I think most important components or ideas have been objectness and using region proposals in weakly supervised object detection, and also um, using prior knowledge and additional cues such as size, equivariance, objectness again, and and also the following the common trend in deep learning. So end-to-end learning gave us better representations customized for the task. Okay, so maybe one common direction, one potentially good future direction is the addressing these ambiguities, and and this can be possibly with improving object measures we have, and also using better additional cues. Thank you very much. I'm looking forward to discuss with you in our question and answering session. Thank you.